right. Hi, everyone. My name is Charles Dawson. I'm a PhD student in Aeroastro in the Reliable Autonomy Lab, and it's my pleasure to introduce Professor Reinhart for the opening keynote. Professor Reinhart is a building scientist and architectural educator working in the field of sustainable building design and environmental modeling. At MIT, he is the inaugural Allen and Terry Spoon Professor of Architecture and Climate, Director of the Building Technology Program, and Head of the Sustainable Design Lab. An interdisciplinary group with a grounding in architecture that helps develop design workflows, planning tools, and metrics to evaluate the environmental performance of buildings and neighborhoods. Professor Reinhart is also a managing member at Solema, a technology company, and served as strategic development advisor for MIT's spin-off Maptwell until it joined Palmetto Clean Technology in 2021. Planning tools originating in Professor Reinhart's lab and Solema are used in practice and education in over 90 countries. I'm really excited to hear this keynote, and I hope you'll join me in welcoming Professor Reinhart.
Good morning, everybody. Thanks a lot for joining us here this morning. I'm really excited to be here. A couple of days ago on the weekend, I told my son, who's a junior in high school and who does robotics, that I'm going to talk at the Robotics Club. And of course, he said, "What do you know about robotics?" And that made me really nervous, especially after I had given you the title, which is probably totally pop culture related, what my thought inclination was when I think about what guys are doing. I had some discussions with some of you earlier today, so I guess I'm thinking of robotics as this broader, loosely defined field between controls and actuators and sensors, and we now try to see how we can put all of that and apply to buildings and the built environment. Let's see if this is working. And as Charles just said, I'm actually from the Sustainable Design Lab at MIT. And what we do, we basically develop workflow and methods. We try to understand how buildings are operated, put together, buildings and cities, and then develop design tools to help decision makers improve their performance. And Solema is a spin-off that commercialized a bunch of the tools that we've developed over the years. So again, coming to my soul searching, what is robotics? I looked to Wikipedia, and basically the goal is to design machines that can help and assist humans. That's, I guess, broad enough. And so I thought, well, the objective of a building is provide shelter from the outside conditions, security, privacy, and keep occupants comfortable. So again, approach this from the perspective of, does this work? If we think of a building as a robot, how can robotics reduce building-related carbon emissions? That's what and feel free to interrupt me anytime. This should be as interactive as possible. And I try to use some of the slides that I often use when I talk about the buildings and climate change, but then infuse some ideas and opportunities where individuals with a background in controls and in sensors and actuators can make a positive, really substantial impact on climate change. So again, I thought about, well, what do we have? We have these three relationships here, and I'm mostly going to focus on first giving a sense of how do we think. And then, as I said before, I'm always going to link this in to what various kinds of robotics could do. So maybe just to frame the whole problem, climate change and the building sector, you've all seen graphs like this. Effectively, the Intergovernmental Panel on Climate Change tells us if we want to keep global temperature rise under 2 degrees Celsius, which is increasingly unlikely, 2 degrees Celsius, then we have a certain budget of CO2 left to use up and release into the atmosphere. And if we are picking 2 degrees Celsius, long-term temperature rise, then we have, that's a good number to know, about 930 gigatons of CO2 left to burn between now and 2050. And by that point, then we need a net zero global building stock. We actually need a net zero global economy at that point. So it's a bit helpful to have a budget because you know how much you can spend. And if we are looking at the building sector is a fantastic 40% of the carbon emissions right now. Kind of shocking, right? So we keep that 40%, but we're going to ramp down like everybody. Then actually a good number to kind of keep in mind, we have 340 gigatons left and 30 years, more or less, to make the global building stock carbon neutral. So that's our budget, that's our goal. Now, of course, the building stock is not going to remain static. If in effect we are projecting right now that the global built area is going to double. And if you think about it, that's also kind of incredible, because it means we're going to build in just 30 years as much as we've built, as Mark Wolfov likes to say, in the last 5,000 years. So it's like an incredible amount of construction going on. I should qualify this. These are the projections, but Ramon Weber, who's coming later, was from building technology as well. We're going to show methods that we want to reduce that number. So, I mean, this is a real worst case scenario. There are certainly parts in the world, Africa, India, where a lot of housing is required. Having in North America are completely underutilized. It's really shocking how empty buildings most of the times are. And so rather rethinking programmatic space reuse, that's a concern. And that can solve as much as making the most energy efficient building you can imagine, the building that you don't build or that you use more effectively. But if I'm going at face value, then we made this real simple model a couple of years ago just to basically create a link in climate change and actions in the built environment. And in our business as usual scenario, that's really not that negative. We basically say that by 2050, we finally figured out that all newly constructed buildings are completely carbon neutral, and that we keep the current retrofitting rate at 1% per year. So globally, we are changing every year about 1% of the global building stock. And if you look at then this upper line here, that's, of course, terrible news, because it means by 2050, A, we are not carbon neutral, and B, we use 2/3 of the global budget for all humans. That includes food production. So that's obviously not going to work. So in order to get to this trajectory, what we effectively need, just to pinpoint it, by 2030, we have to increase the annual retrofitting rate up to 5% per year, so a 5-fold increase. There's some really concentrated effort with the governor of Massachusetts office right now that our lab is trying to organize this and just change the rate at which we are doing and retrofitting buildings. And then equally difficult, by 2030, we need really all new buildings to be completely carbon neutral. And that includes the materials we use to build these buildings. Frankly, we don't know. Some things we know. We know how to build net zero buildings. I'm going to talk about that in a bit. But when it comes to the material choices, there are huge amounts of open questions out there. So this seems nearly impossible, but at least it gives you something actionable that you can work towards. And I think that's really important when you work on climate change, that it's not just, oh, I'm doing a little here, everything's going to be fine. I think having this big picture for all of you is really important. So just really practical, what technology pathways actually do lead you to net zero today? And this is something that I use in an intro class called 441 every fall, which is kind of, if you're interested in this, this is a class for architects where we have a lot of students from other disciplines as well, where you learn how to model, design a building to have a building net zero. So you understand basically all the physics and the modeling that goes on when you want to build something like this. And this is the building we always used. It's like the typical New England home, 1,300 square feet, built in the 1920s. And at the beginning of class, we assume the owners have done absolutely nothing to their building since 1920. They have an inefficient, and here we go. And just to give you a sense of how this would pan out, so from an owner perspective, they pay for utilities and gas, $4,000 a year, and they drive their 40 miles to work, so they have $1,700 on gasoline. And they spend 16 tons on buildings and car usage. To give you a sense, typically, if you want to live in a real just environment where everybody on Earth can use the same amount of carbon, each of our carbon budget is 2.5 tons per year right now. So we're obviously burning that here pretty quickly. So this is how the owner looks at it, money usually. And then this is the grid, how the grid looks at this household. And basically you see here hourly the natural gas use and the electricity use for every hour in the year. And really a key thing that is really, if you're a utility, you want to sell stuff. But ideally, you want to sell stuff at a constant rate. You don't want to have big peaks, because peaks are a problem. Everybody peaks, the grid becomes unstable, so you have to build the transmission lines. These are enormous costs, right? So this is a bad client. What could the client now do? So we're now kind of going on a little journey, how a client could approach this whole topic. And typically, the first thing that we would do is everybody tells you there's an official push from Massachusetts and most New England states right now, get a heat pump. So big idea, electrify heating. What does this mean? We don't want to burn gas. Obviously, we're not going to get towards if you have a line where you burn gas. So we want to use electricity because in principle, all the electricity can come from renewables. That's a pretty easy argument. So if you do that, actually, do anything, I just put a heat pump in, like one of these mini splits, then you halve your carbon emission. That's great. But your costs go up. And that's really important to notice. Even though the heat pump is more efficient, electricity is more expensive than natural gas, so your utility bill goes up. If you want to be an extra goody two-shoe for the environment and you actually your costs go up even more, then in principle you have a net zero building, but your costs are twice as high as they were before. So I'm not going to talk so much about that today, but our lab does a lot on modeling equity, adoption rate, who is actually going to pay for things like this, given the content of today's lecture. I'm not touching on this, but this is obviously excluding large parts of society out of the batch, right? But if we take that even further, so if I'm doing what basically, if I open Google or Netflix, this is the first thing. If you're a homeowner, get a heat pump, get a PV system. If I do what I'm being told and I try to do the right thing, then effectively what is good, I can reduce my utility bill if I have a heat pump and PV on my roof. I pay about $50,000 and I become from a bad customer to an absurd customer. Because what I'm now, I don't buy any natural gas anymore, right? That's gone. So you see in purple, that's my old electricity use every hour. And now I have this monstrosity of a PV system on my roof that's way too big, but it pays me to do this. So go big or go home kind of thing. And so you have basically somebody that dumps enormous amounts of electricity into the grid all summer, but the peak, and remember, peak is really what makes you good or bad, is higher. Because on the cold, cloudy day in winter, when your heat pump is working really hard, there is no solar sun to help you. Otherwise, the day wouldn't be cold. So this is a problem because you increase, typically we say, in New England, right, more than double the capacity of the grid. So that's a really big deal. A, we need a twice as strong grid. And B, we don't know where the green power is going to come from in the winter. But there are all, if you follow the news, discussions with Hydro-Quebec right now to put a line from Quebec, a hydro line to support us in the winter. But some of the other states north of us don't want the hydro line through their territory. So this has been in stay mode for years right now. So we're in a way following a policy that is not fully logical in the sense because we don't know where that electricity. But this is how it pans out, 50 plus a 13-year payback time. And so kind of my big main takeaway or message is really what do we have to do instead? We have to basically renovate our buildings. And so this is basically what we're going through in a class like this, where we say, okay, LED lighting, efficient appliances, thermostat. I'm going to talk more about the thermostat because that's as close to robotics as we get in buildings, a little sad. And then air source heat pump, insulation. We basically have to make our building more efficient. And then what happens then? Then we use so much energy that we can get away with a smaller PV system. And if you look at our footprint on the grid, we are a lot less on the grid. So this is a good neighbor system where basically we pay about the same amount of money. I should say it's a lot more. Doing all of this to your building, especially the renovation, you need a really good partner and a good, very close household to drive that, because right now that process is really intrusive. Everything takes 10 times longer. So we haven't really figured that out. That's definitely the retrofitting market is a market that needs to be changed, disrupted at least. But if we're following this, then the good thing is here we have negative utility bills and our carbon emissions are low. And so this is kind of the ideal that we are striving for, combining retrofitting with PV and controls. Now, actually, the next thing, of course, and that's the smartest thing you can do, you can buy an electric car, because if you're driving it out anyhow, because the PV that's going to pay for driving your car is an enormous saver. So actually, if you just for your own pocket want to do the best thing, and it's good for the environment too, the moment you have basically the PV, you can charge your car every day, that is highly beneficial to you. Now, this is probably where I'm first plea, and I'm going to talk about this a little more in a bit, but this control is right now really dumb. Basically, all that happens right now is the electricity goes from the grid to your car. And so basically, if you have a non-smart sensor, you just plug the charger in, and it just uses huge amounts of electricity. A smart sensor at least delays this until later in the day. But what you could really think about, this battery can drive your building. Your car battery can basically operate your building for several days. So going back and forth between when the grid needs help would create enormous value. Right now, we are not doing that at all, probably due to liability issues. We are not there yet. Even the Tesla Powerwall, even like this kind of pretty innovative companies, really don't have any smart control algorithms right now that basically work better with the grid and integrate it. So there are huge opportunities, and I actually can't tell you why this is the case. So that was basically, so I want to go a little bit now into residential and commercial buildings after giving you a big idea what can be done. I mean, the interesting thing is when you go into manufacturing, I want you to look at this as when you go in a factory 100 years ago and now, the worker from 100 years ago wouldn't recognize the factory, wouldn't know what to do. And it's kind of funny. This is from last week, a building retrofit. So the retrofit kitchens that we make today look actually exactly the same as 100 years ago. It even says we are striving to have a 1920 kitchens. So in a way, you're dealing with clients who they don't want a robot necessarily. They don't want a robotic arm that cracks their eggs. There is kind of this kind of hidden ideas. There's of course some intelligence in all these devices here, but overall you're dealing with clients that might not necessarily want something that looks completely different. And then there's of course the big promise of the smart home. Everybody gets flooded with the latest IoT sensors, and then you get the strange images here. I'm not sure what this is really supposed to do. It's like the blue shield that protects you from the world. And these blue devices are really just glorified remote controls. Like, it's very strange that the control algorithms haven't kept up with the capabilities we even in principle have. Like the best if you go online for these LED lighting system, when you see some guy in a basement then basically has like a psychedelic rainbow on there, and you wonder, that's it? So that there is no smarter ways of how we actually use the actuators that we have in buildings right now. So really the only robot that made it in your home, which is, I guess, a smart thermostat. But what does that really do? If you look at the old thermostat, of course, what does a thermostat do? There's a lot of surprise. Some people think it's a cable. If you put the temperature really high, it's going to get warm faster. It's not true. So it's basically just, of course, it sets a temperature range, and your heating and cooling switch on and off when you're in this range. And then the big innovation of the 80s, 90s, the programmable thermostat was to say, hey, during certain times, you don't have to heat it to keep it as hot and as cold. It took a PhD, probably from MIT, to program this system. So really the main innovation was that the self-learning thermostat tries to do that for you, right? But it hasn't really done much. I think mostly what the smart thermostat does, it tries to learn it, adjusts the schedules a little bit of when you're in the building and when you're not. And then does anybody have a Nest? So when Yeah, so I'm not really sure what the blue, I think every so often I want you to feel good and say, if you now turn the thermostat down a little bit, you get a green leaf as a reward, and then it says, hey, you can live with 75 instead of 76 degrees Fahrenheit. There's really not much. The sensor doesn't think beyond the space. And I just want to show you, just as an example, how much a sensor could think beyond the space. So this was a study we did a couple of years ago. We do this urban analysis where, similar as what you saw before, an analysis of an individual building, we model a whole city, a whole state, actually. Right now we're modeling Massachusetts, every building. And so then we have this load curves, and when you look at the hottest day of the year, this is Prudential Center, Back Bay, Boston, then you basically see this is the electricity use on the hottest day by time of day. And if we were to cover like a third of the rooftops with photovoltaic, then you see the yellow line here. So in the middle of the day, most electricity is being generated. And you see this mismatch here. When we look at this, it becomes clearer. Like if I subtract the yellow curve from the upper light gray curve, then I get this funny shape here. And so the good thing is I reduce the peak. And peak is royalty. So if you manage that, that's a good thing. But what you did at the same time is you created this really large ramp. That means in just 2 hours, in this case, you would have to change the amount of electricity that you provide, nearly double it. Again, the utility doesn't like that at all because, I mean, you want things just running and humming along and being happy making money. The worst thing you want is for something like this, you suddenly have to call your extra providers and say, in the next 15 minutes, please turn on your devices, your peaker plants. That's expensive. That's usually not very clean. So this is not the curve that you want. Now, what you could do actually for free, if we were just to have controls over thermostats, and you can control the thermostat within 3 degrees Fahrenheit, most people in a building wouldn't even feel that. You could basically, for these 2 hours, just tunnel through this. So this is just like an incredibly simple device that would, for free, with some algorithm, some control lines, reduce your peak by as much as covering a third of all rooftops with photovoltaic. So that just gives you how big that is. So after the paper that, it's still, we could go a lot further. Smart learning thermostat could basically train and understand their building over time. So imagine your thermostat does some experiments. So every night, or when they know nobody's in the building, they're like Hall, but in a benign way. They basically train your temperature up or down. And they basically get ramps. How does your building react when it's hot and cold? And when you know that, then your thermostat can really easily figure out what to do to say, if they get a signal from the grid, please save right now. They could do things you wouldn't even realize to your buildings and flatten the load curves that way. And if they then had your electric car there where they take electricity and dump out, you could to an enormous degree flatten the load curves overall. And so, is this robotics? I don't know, but I know this is something we really need to do, and there's incredible value in there for society in general. Like getting rid of, this is, I think, what control theory's best idea is use existing, best application is use existing devices and just make them operate things more efficiently. How long do you want me to talk? I have a lot more, but I want to keep time for discussions.
I think 15 more minutes.
15?
10.
Yeah, no, it's good. I can keep talking, but I want to engage with you guys as well. So just to give you a sense, this is not an isolated New England phenomenon. This is the ISO area. So this is a large electric area for California where photovoltaic is most widely used. And you basically see how over time, due to the electricity use, these what I just showed you in this little simulation study happens for the whole state. We actually call this the famous duck curve. And it's really hard to find a duck. That's really a goose. But to find a duck that follows this line. But whenever you hear that, that's one of the terms that people in the kind of electricity grid controls industry are using. And of course, the duck curve shows you why storage is so important. So everybody who works on cheap electric storage is a hero because basically the renewables are at a point right now where they're only as valuable as any ways for us to mitigate, basically. We don't just need the peak photovoltaic that we are generating. I think Germany, by now, I heard last week from a speaker, last year had 400 hours, and I'm not from a sunny place, where 400 hours in the year when photovoltaics created more electricity during this 400 hours than the grid can take. At that point, you get paid to use electricity. Crazy, but it's true. So this is when suddenly things such as charging batteries, battery that has control to charge is very valuable. And of course, there's a lot of theory, if you look at the work from Les Norford at MIT, that's called model predictive controls, where we predict what's happening, so we're the curve. So for example, you can buy an expensive Powerwall battery, or you can just cool your building to the lowest possible level. And then everybody might come in, what do you do to your building? You're wasting all this energy. It's actually really good. And you have excess power, you ramp down until people are nearly freezing in the building, and then you let it basically go through the peak. Right, things like this are incredibly valuable. You basically use the concrete in the building as a thermal battery for your building. So there are just enormous opportunities when we work together on that. And I mean, a lot of that new, but it's not happening. It's really surprising in a way. So I think this is more or less what I talked about before. So I have two more topics. I want to talk about the campus because we're all at MIT. We should make the campus better. But I had just some musings about, this is my office. Hasn't really changed. Whoever was in my office in the 1920s, I think it was a bathroom in the 1920s, but whoever had been in my office would probably have a really easy time. I'm not sure, this is probably from the 1960s, if I'm lucky, my light switch. This thing, I actually don't know what this does. It doesn't work, despite my paints or my indications. So the thermostat does nothing. The window works, but we used to, in the 90s, have been open in the main group to open. We had this double hung windows. MIT was built to be well and well naturally ventilated. That's kaput. So all the windows are basically shut tight and have a window the size of a shoebox to get some fresh air. But overall, at least I can adjust my comfort. And we know people are more happy in buildings when you adjust comfort. This is where the building technology students are sitting. There is one thermostat for everybody. There are thermostat wars, basically, which happens all over the place in open offices. Right control, some person is cold, some person sits right there when nobody looks, changes the thermostat. That happens. So a couple of years, a company tried to overcome that. I'm not sure if you know them, look them up. They're coming out of UC Berkeley, Comfy. And when they started off, they basically had, everybody has an app. You're nothing without an app. And then basically the apps ask you, are you warm, are you cold? And then it allows you to switch. And I looked at them this morning. This is actually, full disclosure, an old image because so the golden days, they raised $8 million in 2016. Now, that's what they do instead. So they even don't talk even about temperature control. It's all about how do you use a space more effectively. So it's a bit sad. I mean, this is also something, as I said earlier, using space efficiently is a good idea. But it also shows, well, for some reason, these automated controls didn't go very far in buildings. And I wonder why that is. So these are my musings from this morning. I hope there aren't too many typos in there. So it's funny because we know occupant satisfaction is obviously key. If you want to have some numbers, per square foot in a typical office building, you pay $300 in salary. You pay $30 for mortgage and rent, and $3 for energy. Energy is not a bottom line number, unfortunately. It's really in this country. It's really the salaries. So the thing is, we know that if you give people controls, they're happier. And happier means work better, means my salary money is spent better. That's at least how the theory goes. So it's really surprising that pivot, but I think it's partially because most buildings still haven't kept up. Kind of my theory from the beginning was the buildings are the same. I have less control than I would have had in my office 100 years ago. We just don't put controls into buildings. And part of this is that, and I don't get it, nobody can explain to me why, but when you get Johnson, Siemens, any large building management control sensor, you pay a respectable $1,500 to have it installed. It's just shocking. And I don't get it. I think partly, and that, of course, is a huge ticket item. We could give everybody in the room an iPhone that could control this better effectively. The thing is, including MIT, there's a lot of resistance to putting wireless controls in there. I mean, if you look at this atrocious thermostat that I have in my room, you could easily, and obviously put wiring in there is very expensive, but you could basically just have a wireless control center right now that does the same thing. And then you find people could come up with a better algorithm to keep my office more comfortable. But there's a lot of resistance. I think it's because of safety controls. When I hear that, I tend to say, this thermostat doesn't do anything to begin with. I wish somebody were to do something to the temperature in my office. So again, I think there's a lot of opportunities here. I wanted to jump ahead and talk just a bit about the campus and what we're doing here and how some work could plug into that. So we had this term, you probably don't follow this. If you do, that would be wonderful. But you've probably heard that our president is really committed to climate change. In her inaugural address, she really wanted to push climate change, and there are a lot of activities. We again say, hey, let's decarbonize the campus. So by 2050, we want to be at carbon neutrality. So we have a work group, and at the same time, in order to kind of advance what happens in the working group, I give the seminar called Decarbonizing the MIT Campus. And our goal there is in line with the very beginning, what would be valid pathways to get our scope 1 and 2 emissions for MIT down to zero? At what cost, what risk, how fast? And just scope 1 and 2 emissions are basically, this is energy that we are directly burning on campus, such as natural gas, so emissions coming from that, or electricity that we purchase, for example. That would be scope 1 and 2 emissions. This is the sad graph of the last 10 years, which shows there's a lot of dynamics going on because we added a lot of buildings, but the carbon emissions haven't gone down. And this is if you go to Energize MIT, all of you can go there to see that and how that works. It's just really, really hard. But of course, if we can't do it, how can we talk about the globe and everybody else? So it's a really big effort. So in the seminar and in this working group, we are basically looking at 10 technologies, some of them that we can buy today, and some of them that we could implement at one point in the future. And then there are, of course, things that we can't control, such as how the electric grid is going to decarbonize and so forth. If you learn more, we're going to release in 2 weeks a report on this. And nobody reads a report. What does everybody do? Play with a dashboard. So we built a dashboard where we have 100,000 futures for the campus. So we say in the report what we should do, but nobody, again, play for it, figure it out yourself how this works. So here we are basically looking at how is our campus operated. And so here are all of our buildings. Right now, what happens, we have the central utility plant on Vassar and Albany Street, between Albany and Vassar Street. We buy a lot of natural gas and a little bit of electricity because we burn that natural gas in a tri-gen plant, and we use, which is when you use natural gas very efficient, it basically creates steam and chilled water and electricity at the same time. So we are our own city. So we have our own utility. And then we have loops that the buildings use. Now, if we were not to do anything, then this is our 186,000 megatons that we use per year. Then even if the electric grid decarbonizes, we wouldn't decarbonize with the grid. That's a really important idea. Why? Because we burn our gas as long as we keep burning gas, we can have the cleanest grid in the world. Nothing's going to happen, right, here. So that's a real problem. But I wanted to first, so if we do the same type of temperature control talked about, this is what this would do. So just get some Nest-esque controls in our rooms would have quite a big effect. What space type do you think at MIT uses the most amount of energy? Biolabs, exactly. Not the robotics. We cannot all get even close to using that much energy. Why is that? Well, it's for a good reason. If you look at any buildings that have these stacks here, these stacks are huge, and they're called fume hoods. And what effectively happens, this is a kind of, this section explains exactly what's going on. We have a space where we might have very toxic material that come out at any moment in time. So to keep that space safe and conditioned, we have enormous ducts. In that class that I mentioned, at one point we walked through a duct. You can drive 7 buses to the ducts of the Nano building in parallel. It's just mind-blowing how big these ducts are. If you've not been to the top floor of the Nano building, it's a tour that's going to change your life. You think you're in a Greyhound station. And it's enormous because you pump enormous amounts of air. This air has to come straight from outside. So if it's cold, it has to be warmed. If it's humid, it has to be dehumidified. So that because the people here want to breathe acceptable, good indoor air quality air as well, like everybody else. So they get this, and then basically it gets pushed out of the fume hood, and these things are like turbines that shoot the air, because it might be toxic, as high up as they can so that it doesn't mix down again. All makes total sense, right? And we want this to happen. I would say the single biggest opportunity is making sure these things stop when they are not being used. It's the biggest control. If you want to do anything good for the world, become incredibly rich. And at this point, I made a case how an office building energy use is so important. This is important. This is a lot of money and energy that we are using. So anything we could make this better would be great. This is a technology problem, but it's also, of course, a problem, a challenge, a human behavior challenge. People are used to do work in a certain way, and it's very hard to overcome. And understandable, safety, this is very important work. But this is probably the single largest things where better controls would just help. I even say you could have a control that just annoys the PI and sends them an email every 5 minutes at night when a fume hood is open, so that the next time the fume hood is closed. I mean, these are real big effects. What would that do to our campus? This is how much it would change. So it's, again, I mean, we're talking controls could make an enormous contribution overall to campus. And we need this along with a lot of other things. So if we actually, just to give you the full story before, and what is the kind of vision for the campus? So we retrofit building, meaning we insulate the buildings a little bit, LED lighting, temperature control, ventilation control. That's going to get us here with a decarbonizing grid, so 50% reduction. Yeah, and by the way, we cover the roof with photovoltaic, but different to what I showed you for the residential building, that's more a token. It's nice to have, our energy use is so high in those large buildings. I mean, I think we should do it. It's a very small effect of photovoltaic, 5–6% maximum. So then really what we will have to do, and you see that a good amount of other universities are doing that, we basically have to dig out the connection. We have to change the connection between the central utility plant and the building. There are actually 2 things that we can do. First, we change from what's called steam. We are changing to hot water, which thermodynamically is pretty clear. If you have pipes that are older than us, older than me, that are in the ground and that have a bit of insulation from over 50 years ago, then they lose a lot of heat to the outside. So delta T is never great. And so if we are basically setting up the buildings to, instead of steam, you just use hot water, then that is a saving in itself. And then we can distribute the heat. There will be a lot of talk. Some of you, if you're interested in it, will hear probably some debates, because what you could also do is have what's called an ambient loop. So you have one building of warm water under one loop of hot water, and you have heat pumps that link into that hot water or cold water, and some buildings that heat dump, take heat out of the loop, others add it to the loop, and that way you're sharing coincident loads. It's actually not a huge difference. We'll see what's gonna happen. The difference case you can think about, every MIT will have a basement full of heat pumps. The other alternatives, we have a cup full of huge heat pumps. And there are pros and cons for both. But the effect is obviously really good. So the last thing that I leave you there for that is, so this only works if our grid decarbonizes in New England. So we are completely dependent on the grid. And we are, of course, adding massive loads to the grid. So if we think about the homeowner, that's not a good neighbor scenario in a way. We are basically probably nearly doubling the capacity of what Cambridge needs without the Harvard campus if we're doing things like this. So this is really a high load that we would be adding. So this is why MIT is looking at a few other things. Basically, the two ones one is nuclear batteries, one is deep geothermal. These are technologies that are nascent, even though nuclear batteries is basically a friendly work for a nuclear power plant that fits into a shipping container, which will be available within the next decade. It's pretty sure that this is going to happen. So there's a variety of attitudes toward nuclear energy. It's fossil fuel, and it's a great base load. So that would solve the problem. Basically, and with a nuclear battery, you can create heat and electricity. And that's my personal favorite. It's totally Star Wars. There are people right now that try to use microwaves to shoot holes in the ground that are 20 kilometers deep, like 12, 15 miles deep. And if we could do that, then of course, anywhere on Earth, and there's some serious money invested. And of course, the whole drilling industry is in love with that idea. Because right now, we can already go up to 4 kilometers deep. That's technology. And at 4 kilometers, you already get warm enough water to heat the campus. But if you go that far deep, you get infinite amount of steam. Well, I would always be very careful when anybody says infinite. But in principle, you get enormous amounts of steam from there. So you can run, basically, you get a renewable electricity from the ground if you do that. So these are, I think, the kind of thing that our institute should be looking at. It's not clear if we're going to drill that here. But these are basically alternative ways if we really want to think of this campus and getting it net zero somewhat. Yeah, key messages. I think there are lots of opportunities in buildings to innovate, even with just existing sensors. I think developing new sensor components that you can retrofit or add to buildings at a low cost could have an enormous impact on buildings overall. And definitely worthwhile looking into. 4401, 4464, that's the class. If you want to learn more, we are super interested in working with you, basically. Since you're learning how to simulate a building, you can put your own control algorithms on top of that, basically, and start innovating pretty much right away. And with that, while we are talking, I leave you. Do you all know the shady algorithm? That's the only thing that comes out of this sea sail, out of this illustrious place where we're in right now. This is supposed to be a personalized shading system of your peers designed a couple of years ago. This thing is supposed to know where you are. It knows where the sun is. And so it crawls up in a non-threatening way along your muons. And then in a second, you will see when it's done, it'll provide you with, I don't know. I have to speed that up further, that movie. But in a second, you will see the shading device deployed. The advantage of this you could have if you have 5 people in the room, 5 of them moving around. And if you want the shading, it would just shade exactly you. So in a second, you will see that opening. And with that, I thank you. So happy to discuss.
Yeah, I think I definitely have some questions.
Yes, that's great.
Go to the audience. So First of all, thank you for your remarks. I'm curious to hear a little bit more about the adoption story for smart thermostats.
Yeah.
And to give you an example, 3 days ago, I got a letter from Eversource
Yeah.
saying that if you install a smart thermostat, we'll pay you $40 a year to turn your AC down in the summer. But
that's great. So, I mean, it means this is finally happening, right?
Yeah. The challenge is I rented a triple decker, and so we don't have central air. We don't have our thermostat. I think is from the 1960s.
So what does it do?
We're not eligible for the program. So.
I thought if they don't check, you should definitely do it.
Yeah.
No, I mean, of course, ideally this would be linked to a building. And I mean, to give you a sense what I would ideally do if I had controls of it. That right now, probably they just know whenever they pay you so that when they are in a crunch, they basically just turn off your thermostat, right? That is kind of the brute force approach. If you were to, as I said earlier, kind of train your thermostat and you want to know ramp up time. Every building has some thermal mass. So ideally you have a building that heats and cools, where the HVAC system is actually big enough to maintain that level. A building where you can basically relax the temperature so it can get a little warmer in the summer, for example. And then if you have more thermal mass in the building, then you could do it probably for an hour. So in an ideal case, they would say, we might pay you. Can we run an experiment on your building? If you have a good building, like if you invested in a lot of thermal mass, then we're going to take you.
Yeah. And I'm sure there might be people here who work on these like system identification problems of trying to estimate those dynamics.
Yeah.
A question that I have, and a second question is about the user experience for the occupants in these smart thermostats, which is there's kind of a spectrum of experiences you can provide from totally invisible, like you don't even think about it and your building is perfect, to something that's a little more active, like the green leaf on Nest, which is come and take some action. Do you have a sense of like where do people fall on the user experience that they want to see from their buildings?
Well, I think people are very different. I would generally say, I think a lot of people just don't want to think about their building at all. And this is where these automated controls can really come to bear. Right? And then others are tinkerers and they want to adjust their levels. We know there's some really beautiful studies from the UK preliminary that if you give people control, it's as if you can get away with a way larger temperature comfort range. So it's like you take control of your own destiny, and if I'm sweating, it's my own making kind of thing. There's a surprising amount of that. The same thing for the whole comfort theory treats of air-conditioned building and the naturally ventilated buildings differently. So in a naturally ventilated building, no AC, openable window, we assume in that model that if it has been warm outside, people will realize, well, it's been warm outside, it's probably warm inside, so that they just accept pretty substantially higher temperature than they would otherwise.
But because they have control, they feel like that deviation.
That is okay,
Yeah, that's really interesting.
Yeah.
So then another question that I have is, what does you mentioned that for these commercial buildings, sometimes it's a big expense to install these systems.
Yeah.
Is it also a big expense for residential buildings? Or?
Well, no, I mean, I think the reason why the Nest is so heavily pushed, I think typically right now is it costs $150, you get 50 or 80 or whatever dollars from Eversource. That's because they usually pay for themselves in less than a year. And they also save, it's actually pretty hard when you use natural gas it means you save enormous amounts actually because natural gas is so cheap. So these systems actually work pretty well. They could just do so much more. And I don't know, I mean, that's really still befuddling me. I mean, I buy any smart gadget that I can and I usually rip it out then 2 months later because like the light didn't really work, all these things get pressure from the rest of the family to take it all out. But it's funny that the systems are not better, smarter integrated yet. Or maybe, I mean, like what you were just describing, that the Eversource has these programs.
Yeah.
It's probably brute force, it's starting, right?
Yeah, and potentially it's something like you mentioned the user experience, and most people don't think about their buildings. The downside of that is people don't think about what upgrades that they could make, I imagine. So it never crosses their mind that I could be saving on my utility bill.
There's really funny work about lighting and temperature. Like if you automatically control it without telling people with how much you can get away. There was a real fun experiment in Canada where people were in a room, electric lighting, and they were just for 3 hours in their room to do, as a human subject experience, do some work. And they had even a dimmer at the side where they could make it brighter or not brighter. And the lighting was dimmed really slowly, like a few percent every minute. And people were pretty much sitting in the dark in the end. But nobody realizes that. It's totally shocking. If you don't have a reference to a window or so forth, it was stunning. There's 25 subjects or so. Mm-hmm. And what do you do with that? Well, it's probably not a good idea to have people sit in the dark, right? And then they did a similar experiment with temperature. And there's also, it's like the frog in the water. And that is not even true. You can boil people and they don't know it. So you can slowly ramp up. That's probably only something you should do when in need, right? But that would be a demand. That was paid by utility for demand-side management.
And I guess it just speaks to the amount of headroom there is for optimization.
Yes, exactly, yeah.
So I'd like to open it up for questions from anyone in the audience. We can have a discussion here.
Hello.
Hi, my name is Soumya. Thank you so much for the talk. I had a question on incentives for retrofitting. Mm-hmm. So I guess my first one is renters and the second one is utilities. So for renters, which I think is like the majority of people I know in Cambridge, Boston, Somerville, we pay for utilities, but then I'm not incentivized to make a retrofit because it seems to pay for itself over a long period of time, but I'm renting, right? I might move in a year. Meanwhile, the landlord is the one who could make that retrofit, but they don't pay utilities, so they don't see that financial gain. So is there any work being done on how we align these incentives better?
That's the hardest problem, the split incentive. It really is. I mean, a lot of our adoption work has focused more on homeowners. And in the country as a whole, the rate of homeowners is higher. Actually, the majority of people own their home or the bank owns it for them. In here, obviously, that is not the case. But it's a huge problem. And a lot of our adoption models right now show that with current incentive structures, well, first of all, it's the higher income households that do it. There are really high incentives for photovoltaic. It's nearly exclusively being picked up by high income homeowners. The heat pumps are so expensive right now and such a pain to put in that it's only high income households. So, and then the whole thing that I talked about with the electric car and the Tesla. So I think it's very likely that unless and this is what we are trying to do right now, if we are changing the rate structure and the incentive structure, we kind of end with this, with Zach Berzola, who just graduated, we called it this the two tails of America, that basically there are parts of America that have no utilities, that are completely independent, and the others, there are fewer people that share an old infrastructure. We're kind of in this funny moment right now where everybody, rich and poor, lives in similar buildings. Of course, there are buildings that are really unhealthy, but a lot of us, like a really expensive mansion in the US is not necessarily more comfortable than a normal house, which is a little funny, but that's the case still. And this is changing now, I think, but it's just gonna drift us more apart. So it's a huge problem, and a lot of people try to do that. In a way, you have to, I think legislation is the only way. I think a rented space, a multi-unit residential, is a commercial building, and it should be subject to all the commercial building regulations, which is typically not the case right now.
Thank you so much. And then the second part was just on the utilities incentive. They would make less money, I assume, if we all retrofit because we're using less electricity overall. So are they kind of helpful in this retrofitting process, or are they antagonistic, or are they neutral? Because I've heard
you asked the hard question. Yeah. So, of course, if you think of yourself as somebody who sells kilowatt hours, then every kilowatt hour more I sell is good for me. At the same time, if I am, as I'm right now in a market where I legally have to take photovoltaic, so I used to have this nice flat line and could just sell and make money. I'm moving towards a market where we have enormous fluctuations. So it's clear. I mean, utilities are a funny thing. On the one hand, they are private, and for everything they do, they can give themselves 9 to 12% profit. That's great. And on the other hand, they have to do what the regulator is saying. So right now, if the regulator is telling them something to do, they have to comply with that. And usually the way the incentive programs work, there's just a certain budget that is set around that they have to pay for that. In the long run, of course, I mean, the good thing is I think utilities were a little boring in the past. I mean, it wasn't so interesting, I would say, like to work for a utility, because you get a fixed income. Everything is kind of every year you go 3% higher and you call it a day, right? I think there's a lot of innovation that in utilities can happen right now, because we have to reinvent from people who sell kilowatt hours to those who sell energy as a service. That means we need more complicated rate structures than we currently have. It's really surprising that Massachusetts doesn't have time of day charging like many other utilities. Like, it's the most natural thing in the world to say, it's really hard for us to give you this kilowatt hour. Guess what? It's twice the value. So turn off the washing machine, right? It would be really natural to do that. And that is, of course, the moment when you release capital. That's the first time we would all think about buying a battery. Right now, there's no reason to buy a battery if you are in a part of Massachusetts or where the grid is stable. There's no benefit to you.
Hi, I'm Nauman from MIT Climate and Sustainability Consortium. Thank you for the nice talk. I have so many questions, but I will start with this. Like, you just mentioned that time of use pricing, and there has been some studies in the past that show that if users are left to do these things on their own without automation, they are initially participate in those programs, but over time their participation kind of slows down. So and also, like, there has been over the last 10-15 years, there has been so many things that in research at least happened, like real-time pricing, time of use pricing, and then like some things such as solving challenges of hardware interoperability, such as there was a Home OS from Microsoft and whatnot. But the buildings at the end of the day are still kind of the same in the market. So what do you think need to happen to have all of these actually in place?
No, it's a really good question. And I mean, starting with the first one, there are these interesting home reports. I'm not sure if you got one. A lot of utilities sign up for that, where you get a letter and it shows you this is your energy use and this is the energy use of your 100 neighbors around you that are similar to you. And it's basically private shaming, because we're not allowed to do that. That actually works. It works for, there's a really beautiful work on this, that for about 2-3 months, you save energy, 2-3%, and then it jumps back. So every 2 months, you have to be reminded you're still bad. I don't know what is interesting. There's also a really funny, great science paper that then looked into, well, why are people doing this? People save energy because they think their neighbors care about the environment. It's like really around the corner thinking. But ultimately, that leads me, I think right now, we say in the US, 25% of the population are concerned about the environment. That's not very high. Even our willingness to pay models say, if I would have campaigns that raise this, that would release enormous amounts of activity and capital overall. So I think this is really what has to happen. On the other hand, you know, I'm so befuddled that all these big tech companies, I think Nest was at the time bought for $3.2 billion. And everybody was, what? For a few thermostats. There was obviously the ambition to completely own the home automation market. I would say Nest hasn't delivered. I mean, it saves a bit and looks good, but I don't know why it's so hard. Maybe it's a total failure of us, actually Ramon is here, that the building scientists haven't made. I don't know why. I mean, we have a lot of ideas, and I know the tech industry reads papers, so I don't know why it hasn't happened. Maybe that's the next startup that you all work on. I don't think there's like a hard reason why it doesn't work. I think the sensors are too expensive. To your point, homeowners are willing to just experiment. You buy a thermostat, you don't really care about the company, right? If the company goes down, then you throw out the thermostat and get a new thermostat. If you have a big building and you buy 5,000 thermostat, then that's really not great if that company doesn't exist a month later. This is this built-in inertia that we feel in anything in large buildings. So I don't know. Do you know?
No.
Okay.
I think we have time for one more question, and then we'll have a coffee break and talk more offline.
I love talking about this, so I'm happy to talk. I have to run in a few minutes, but I'm happy if you reach out to talk to you. Hi.
Yeah, hi. My question is surrounding the energy storage problem.
Yeah.
So you were kind of talking about two different timescales. You talked about demand being like this duck curve throughout the day.
Yeah.
And then you're also talking about over the different months and the different seasons, how you have like higher supply curves for green energy. So what are the different storage options available for those different sort of timescales? And what do you think the optimal storage solution looks like?
It's a great question. I mean, electric storage is really expensive. Batteries are expensive. The reason why I was pushing the kind of Tesla electric vehicle is because people just buy an enormous battery. So they anyhow have it in the driveway. So if you have it, use it. And it could really create a lot of value overall. Otherwise, if you think of what a campus would do, even for daily storage, the best is Princeton is putting in right now, Cambridge, Stanford has a very huge system. It's basically water is a great energy thermal energy storage. So they have these big tanks, one for hot, one for cold water, and then same idea, they just cool the tank or heat, they cool one tank, they heat the other tank, and it's just sitting there like a big thermos. And you can definitely, over the time span of probably 72 hours, keep all that energy. And these, we just got a talk from Princeton about this, about their new energy systems. These things pay for themselves in very, very little time. So this is daily, time of day kind of storage. Then the other question was seasonal storage. That's super hard. I mean, there are some, I've never seen the nebulous caves in Scandinavia that are so big that people put in hot and cold water. But obviously, that there are not a lot of caves like this. And then that only works if you're something that is so enormous that the heat losses at the edge compared to the surface to volume ratio has to be to your advantage. Otherwise, seasonal storage, I mean, what people do, another more time of day solution is actually that people pump rivers backward. Sounds really funny, but that's definitely something where you just fill ponds and lakes. That's used for nuclear power a lot. I think there are a whole bunch of Swiss lakes where they buy electricity from France. France has a very high rate of nuclear power, so at night they can't do anything with the power, so they pump full lakes. And then they sell this as renewable energy. Then you have hydropower basically linked to it. These are good ways of doing that. Seasonally, there's nothing really great. This is the problem with the way we try to overcome this is investing massively in a better grid. So Texas, for example, the good people of Texas paid over $2 billion out of their own tax money to connect the west of Texas, where nobody lives, to the east and the eastern shore. Because the cheapest wind that is generated on site right now is in the Midwest right now, these large wind fields. But this wind electricity only pays for itself if you can effectively move it. And so we just need a really strong grid, because people always love to point out the sun is not always shining, the wind is not always warm. Well, the wind distributed over the country, there is somewhere nearly always wind, and especially if you're in the ocean or so. So you need like massive investments in a grid. Doesn't solve the storage problem, but at least it moves energy around very quickly.
Thanks. Well, thank you for the questions and for the discussion. I think we'll cut this short in this session here, and then coffee break. And
coffee's
we'll
great.
Be back for a panel in around 5 minutes. So, great. Thank you.
Super. Thank you. Thanks for having me.
Yeah.